You have seen several examples of linear transformations. For example, a rotation in the plane around the origin is a linear transformation. Rotations have an extra property apart from linearity. They are so-called orthogonal transformations. Such transformations preserve the angle between vectors and the norms of vectors. They play an important role in computer graphics. We will study orthogonal transformations in this video. I'll start with the definition. A linear transformation T from Rn to Rn is called orthogonal if the following holds. For any two vectors x and y in Rn, the dot product between Tx and Ty is equal to the dot product between x and y. That is, T preserves the dot product between vectors. Remember that the dot product can be used to calculate norms of vectors and angles between vectors, so the following theorem should not come as a big surprise. An orthogonal linear transformation preserves norms of vectors and angles between them. But the converse is also true. A linear transformation that preserves norms and angles is orthogonal. The theorem gives a characterization of orthogonal transformations. Before I prove it, let me show some examples. We already saw that a rotation preserves angles and norms, so it is an orthogonal transformation. Another example is a reflection in a line through the origin. This transformation also preserves angles and norms, so it is an orthogonal transformation. But it is a very special requirement. Many linear transformations are not orthogonal. For example, a shear map. The angle between the vectors before the shear is not equal to the angle after the shear, so this is not an orthogonal transformation. Let me return to the theorem and show you why it's true. Let's start with the first part. Assume that T is an orthogonal linear transformation. My claim is that T preserves the norm of vectors. Indeed, the norm of Tx is equal to the square root of the dot product of Tx with itself. Since T preserves the dot product, this is equal to the square root of x dot x. This is the norm of x, so yes, T preserves norms of vectors. Also, T preserves angles. For this part, we assume that the norms of x and y are non-zero, otherwise the angle is not defined. Since T preserves norms, this means that the norms of Tx and Ty are also non-zero. Now, consider the cosine of the angle between Tx and Ty. This is equal to the following: Tx dot Ty divided by the norm of Tx times the norm of Ty. Since T preserves the dot product and norms, this is equal to x dot y divided by the norm of x times the norm of y. This is the cosine of the angle between x and y. Since both angles are between 0 and pi, we conclude that they must be equal. This proves the first part. Now let's look at the second part of the theorem. Suppose that T is a linear transformation that preserves norms and angles. I will show that it preserves the dot product between vectors. Indeed, let's look at Tx dot Ty. We can write this as the norm of Tx times the norm of Ty times the cosine of the angle between them. Because T preserves angles and norms, this is equal to the norm of x times the norm of y times the cosine of the angle between x and y. Finally, this expression is equal to the dot product of x and y. As I mentioned before, the angle is not defined if x or y is 0, but in that case, Tx or Ty is 0 as well, so both dot products are 0. The theorem still holds. Since orthogonality is a special property, you can expect that the standard matrix of an orthogonal linear transformation has special properties as well. We will study those properties in the next video.